So just to summarize what we said on the last page, we could think of this basic line integral here as a line integral that only finds the arc length. And there's nothing different between computing this line integral and computing the arc length integrals that we did in Chapter 14. Where we're going to take this line integral and think of it as a tool that we can extend to more interesting ideas is when we integrate it over some function other than just the understood function 1 here. And what we choose to put in place for that integrand is going to have a whole lot of different real-world interpretations. We'll focus on those in class, and we'll get some pretty interesting results. But I'm only going to really focus on this first way we can think about this, where if we think of, first of all, our curve as living in the xy plane, and then we think of the function as some surface that lives above that xy plane, gives us the height, if you will, at a point above that curve. Then when we go ahead and compute the line integral as follows, then what we have is the area of the curtain formed between the surface and the curve. So I haven't used that word curtain before. Let's go ahead and do that. So here's just a generic illustration where here we might have, here's our curve C that lives in the, you can see here's our, here's the y-axis, here's the x-axis. We're in the xy plane here. So the lower part, that curve is in the xy plane. And then we've got some function here, some real valued function of x and y, so that makes it a surface, and you could think of that surface as living above the curve. Well, then when we compute the line integral, when we go ahead and compute the integral over the curve C, so again, folks, whenever you're writing this over a curve like that, you should consider that a line integral of f of x, y. Careful here, folks, we need to have ds. We'll introduce some other parameter. We'll look at writing this differently in a moment. Let me just clean that up, f of x, y, ds. But right now, we develop this tool as a expression in terms of arc length, that parameterization, and eventually we'll want a different parameterization. But anyway, this computes the area of the blue curtain. That's one interpretation, and it's not by any stretch the most interesting interpretation, or even necessarily the most useful one. But what I do think is it is an interpretation that we can quickly visualize, and that's why I wanted to do it in the pre-work for today. So we will see many other applications. For example, if instead we think of as our curve as existing in XYZ space, and if that curve represents some sort of wire, and say we've got some real valued function of the point in 3 space, so some function of x, y, and z, then we could think of that as outputting the density of the wire at any point in space. And so when we go ahead and compute the line integral, it'll find the mass of that wire. So there's another interpretation. These two interpretations are kind of familiar to us calc students, and the book is going to call these, and we'll call these scalar, we'll just say scalar line integrals. That's good enough room to fit that in there. So scalar line integrals. Other books will sometimes call these specific ones path integrals, and so I just thought I'd point that out to you. So these two types of integrals, where we're thinking of this function right here as initially just being some scalar valued function, have the most immediately recognizable applications. But we've now introduced the idea of a vector field. And what we'd like to do is we'd like to think of these curves, curve C, as sitting somewhere inside of a vector field. And then we'd like to do some sort of meaningful integral that involves both the curve and the vector field. And the most natural one to pick is this one here, where we're going to take the vector field function and we're going to dot it with the unit tangent vector of the curve. Notice that if we're dotting it, that is going to give me a real value, but we're going to go ahead and integrate over that dot product. And so we can think of that as a line integral over a vector field. In this case, we can think of this as maybe being the work done as we push an object along the curve. through this force field. So if our vector field is a force field, and we have some object and we push it along the curved path, then we would be computing the work done. We will also introduce something called circulation in class, and so really computing circulation and computing work are really the exact same computation. Anyway, our book is always going to consider this type of line integral. It calls it a line integral over or of a vector field. And again, what are we doing? We're taking the vector field description, that function there, and we're dotting it with the unit tangent vector of our curve. So that's something that we'll see in class here and when we do this as a group. And then finally, if f is this function, if we think of f as f dotted with the normal vector of our curve. So again, if we've got some sort of curve here, here's maybe C, and we could, everywhere along this curve, we can compute the normal vector. That's something we've learned how to do. And then if we dot those normal vectors with, maybe this is our vector field here, if we dot those normal vectors with our vector field at a particular point, we've again got some sort of scalar that we can add up in a similar manner, and this is going to compute something that we're going to call the flux. So we'll see all of this as we go into our next class. But sort of the take-home point for today is that regardless of what interpretation, so we could have many different interpretations, many different functions can go here. But sort of regardless of what function we choose to put there, we still have this line integral form, which is very nice and compact. It really packs a lot of ideas into a little space. But what we'd like to do is we'd like to actually manipulate this somehow. We want to actually compute these. So how are we going to do that? Well, what I'd like to do is remind you of something we saw way back in chapter 14, where we introduced the arc length function. And we thought of s of t, the arc length of a function, was the integral from a to t of the magnitude of r prime of t. Oops, and I need to be a little bit careful here. We need to introduce a dummy variable. So r prime of, let's say, tau d tau. So this was something that we developed back in chapter 14. And again, if you're rusty on that, or if you're curious about that, go back and watch those that video on arc length that I mentioned at the beginning of this video. Well, something that we did at the end of that video was we said, okay, well, we could go ahead and differentiate both sides of this with respect to t. And if we do so differentiating both sides of this with respect to t, I'm going to do that in red. Should be a tau. So on the left-hand side, we will just get simply ds dt. But on the right-hand side, we've got a fundamental theorem of calculus problem where we're taking the derivative of this this particular type of function that is that if you go back and review the fundamental theorem of calculus part 1, it is this type of function. And it says if we want to differentiate it, what we end up getting is simply the integrand evaluated not at tau any longer, but at t. So this is something we developed in chapter 14, and then applying the fundamental theorem of calculus to both sides gives us this expression, and I can go ahead and solve this for ds formally, and if I do so, we end up with this expression right here. And so that gives me a nice way of manipulating the ds that showed up in our line integral. So I can rewrite our line integral as the integral of c of f of, now here because I'm applying some sort of parameterization to this, I need to put f of not, x and y and z or whatever, but this needs to be f of r of t, and then times the magnitude of the derivative of our parameterization, dt. Oops, and I should be more careful here, because we now have a parameterization, the parameterization would go from a to b. So this is for r of t, a parameterization of c on a less than or equal to t less than or equal to b. So folks, I know this has been a long video. We're just about done with this first part. And the last thing I want to say is that for us to be able to evaluate a line integral, even though the interpretation of f is going to change in all of these examples, the steps are always the same. So what we need to do is to find, whenever we're asked to compute something like this, we need to first find a parameterization for c. Now sometimes I'll give you that parameterization, or the textbook will give you that parameterization. Other times you need to be creative and come up with the parameterization. So if students get stuck in a problem, it's usually actually this very first part, which has nothing to do with the new material, and that is they get stuck coming up with that parameterization. And we'll talk more about this in class, but sometimes we need to make sure that we've got the correct orientation for that parameterization. The next thing to do is compute this speed component. Remember, this is the derivative of, if we think of this as a position function, this is a speed component. And then we can go ahead and evaluate this integral this way, and this is what we just sort of derived here. So this is kind of your keeper formula for doing our line integral calculations. So folks, we'll pick things up in the next video, where we will actually evaluate one of these line integrals. So stay tuned for the next video.